Good afternoon, dear students. Today's class we are going to discuss about Graham's law of diffusion. So from this Graham's law of diffusion, to understand this Graham's law of diffusion, we should understand two concepts. That is, first one, diffusion. Second concept, effusion. Both are different concept. So diffusion means what? What is diffusion? Movement of gas molecules. Movement of one gas molecules through another gas molecules. So movement of one gas molecules to another gas molecule. Okay, so this is known as diffusion. So how to understand diffusion? For understanding diffusion, we are going to take one system. So in this system, we have two parts. Okay, in this system we have two parts. Now these two parts are connecting with the whole. Okay, connecting with the whole. We have one system. In this system we have two parts. We have named this one is A and B. A and B. Now filling this, first close this hole in between these two parts. Now we closed this hole. Okay, we can connect this two part with the hole. Now we closed this hole and fill A part with one gas molecule. Okay, some certain amount of gas molecule is filled in the part A. Then again filled part B with another type of gas molecules. Okay, with another gas molecules, not a same molecule is filling in the two part, but they are different gas molecules are filling in these two parts. Now we can see this one. This is A gas and this is B gas. Okay, we named this is A gas and this is B gas. Okay, so just named like this the gas in the first part and the second part in the same system. So what are the characters of gas? They can flow from they can move from one place to the another place. So when you open the closed room, then you will that air particles or gas particles are present in the closed room or going out, or they are moving from that closed room to the next open part. Okay, so this is one of the character of gas molecules. So again this character is using, or it is playing a main role to understanding diffusion in this Graham's law of diffusion. So gas have the capability to occupy some open space and also some gas filled space. Okay, so just imagine a room of your home. Just close this and open the window of that room. What will you get? You will get some air from the outside of that room through this hole in the window. Okay, so like the same one, diffusion means what? The air is moving from one part to the another part is diffusion. Okay, so the movement of air particles from one part to the another part, or we can say this is from the region of higher concentration to lower concentration. So now you will get in the closed room, from you are inside that closed room, so you will get some fresh air or some air particles from the outside through the window. So this process is known as diffusion process. Okay, just understand like this. When air particles is coming from higher concentration to the lower concentration is known as diffusion process. Okay, it's not a different one, it's the same one what we are experiencing in our daily life. Diffusion means movement of one gas particles from one place to the another place. So simply you can say what is diffusion: movement of air particles or movement of gas molecules. Okay, so this Gregham's law of diffusion is explaining the movement of gas particles or air particles. That moving gas particles should be non-reactive gases. Okay, they should be non-reactive gases. So why it should be a non-reactive gases? Because if they react together, then it will produce a new product. Okay, but here we explain, or Gregham's law is explaining only the physical property of gas particles, not a chemical property of gas particles. So when the two molecules of gas are reacting together, that will explain the chemical property of the gases. But Gregham's law is explaining that here the physical properties of gas. Okay, physical properties of gas. So in the diffusion process or the effusion process, the air should be the condition of air is non-reactive gases. Okay, they should be non-reactive gases. Now take this two part like a room and like outside. Okay, now you can open this hole in between these two parts. Open this hole. Now what will happen? By this hole, this air particles are moving from the B compartment to the A compartment. So they are moving through this hole and they are diffused with this air particles. Now this air particles, generally gas molecules, mean they will move from one place to the another place even by a small hole. So this gas molecules also moving through this hole, this small hole, from A compartment to B compartment. So what is happening here? This A particles also moving through this hole. Okay, so now this is also filling in the B compartment. This process is generally known as diffusion process. Okay, diffusion process. So what is diffusion process? Mixing together non-reactive gases by the movement of gases. So how they are mixing together? By the movement of gases. So what is the movement of gas? Gas are moving from higher concentration to the lower concentration area. Okay, higher concentration area to lower concentration area. Now before opening this hole, this is a higher concentration of this gas particle A, and before opening this hole, this B compartment containing the B gas is a higher concentration one. Now because of opening this hole, due to this hole present in between these two parts, the air particles are diffused together. They are diffused together. That means diffuse means what? They are moving from higher concentration area to the area to lower concentration area, and these particles are higher concentration area to lower concentration areas. Okay, so this is diffusion process. And next concept is effusion. So what is effusion? In the diffusion, you know that the movement of gas with another gas with another gas. Okay, so they should be a non-reactive gases. In the effusion process, the gas the concept of effusion is gas is escaped from the container. Okay, gas is escaped from the container through a small hole and filling into a vacuum place. Okay, and filling in a vacuum place. So you can take a system to understand the effusion process, like the system we are explained here. So take a system which contain two parts. This is A part, this is B part. Okay, A and B. Now fill A part with the gas. Okay, with the gas, any gas. Okay, filling with gas. This A part is completely filling with gas, but B part there is no gas molecules are present. That means what? It is a vacuum place. It is a vacuum place. It's a vacuum place. See this one. A is filled with a gas particles. That means air filled part A. B is empty part or a vacuum place. Okay. Now make a hole between these two parts A and B. Okay. Between these two parts. Now you made a hole between these two parts. Now what will happen? You know the gas particles contain the property they can move from one place to the other place by a small hole also. Okay, so they have the ability to go or to move from one place to the another place without help of any other third force. Okay, so we can so this, if you make a hole or if you made a hole between the two parts, this can easily move or they can easily escape. Okay, they are escaping from the A part and filling into B part, trying to filling in B part. So this escaping process, okay, it is only the escaping process. This is known as effusion. Okay, this is effusion. So what is effusion? Gas particles are escapes from the part from a part to empty part or empty place through a small hole is known as effusion process. So this is another process. So diffusion is a different process. They are mixing together two gas particles, but effusion means they are escaping. Only the gas particles are escaping from the higher part to the vacuum place or the empty place. Okay, they are trying to fill the gas into empty place. Here Graham is relating rate of diffusion and rate of effusion. Rate of diffusion and rate of effusion is not a difficult one, it's an easy one. Diffusion process, so how much it's taken in the diffusion, okay, in two gases, how much diffusion is taken place and how much effusion is taken place in a gas. Okay, so that amount is it is explained or which we taken by rate of diffusion, and the effusion amount we taken by the rate of effusion. Now Graham is relating this rate of diffusion and rate of effusion through with the molar mass square. Okay, so the root of molar mass. So relating rate of this is Gregham's law of diffusion. You have to write like this: rate of diffusion or this one or this. Okay, rate of diffusion or rate of effusion. Okay, you do not taking place the both the process in one reaction. It is only it will take only diffusion process in a reaction or effusion process in a reaction. So take rate of diffusion or rate of effusion. Rate of effusion is, okay, this rate of effusion and rate of diffusion is inversely proportional. Okay, inversely proportional to root of molar mass. So molar mass means the gas which is taking place or which is undergo the reaction of effusion or diffusion. Okay, so the molar mass of that particular gas, the root of molar mass. So rate of diffusion or rate of effusion is inversely proportional to root of molar mass. Square root of molar mass is known as, or this statement is known as, Gregham's law of diffusion, or we can say this is Gregham's law of effusion. Okay, so now we can write a mathematical form for this Gregham's law of equation is mathematical form. Rate of, first we can write for rate of diffusion. Rate of diffusion inversely proportional. So 1 by, okay, inversely proportional 1 by root square root of molar mass. So square root of molar mass. This is Gregham's law of diffusion formula. So rate of diffusion is inversely proportional with square root of m. So how to write it for effusion process? Rate of, it's not given in your book. Rate of effusion inversely proportional with root of molar mass. Okay, this is the equation for rate of effusion by Gregham's law of diffusion. So in Gregham's law of equation or diffusion, we take two gas particles. So this is undergo diffusion process. So how to write this two gases by Gregham's law of equation? Rate of diffusion, that means rate of gas A, rate of gas B. So rate of A divided by rate of B equal to root of 1 by root of m, capital M, molar mass. Now we can write this: rate of A is RA divided by RA. Okay, rate of gas A, RA divided by RB, rate of B equal to root molar mass of B divided by molar mass of A. Then when the diffusing gases A and B under the different pressure, okay, so we treat this system under the different pressure. So rate that first A gas filling in the first compartment, it's have the different pressure with the second compartment. So first compartment P1 and second compartment P2 pressure. Gas A and gas B. Okay, now see this gas under pressure P1, this gas under pressure P2. So they are under the different pressure. We can write the Gregham's law of diffusion. RA divided by RE is equal to PA pressure of A, PA divided by PB root of MB divided by ME. This is the equation which is derived from Gregham's law of diffusion for different gases A and B under different pressure PA and PB. You know all the components which is involved in this reaction. RA means rate of A gas, RB means rate of B gas, PA pressure of gas A and PB pressure of gas B, MP is molar mass of gas B, MA is molar mass of gas A. Take page number 168 and mark the question. What is diffusion? What is diffusion process? The property of gas which involve the movement of the gas molecules through another gases is called diffusion. And what is effusion? What is effusion or effusion process? Effusion is the another process in which gas escapes from the container through a very small hole. This is what is effusion. Then write Gregham's law of diffusion. So for writing the Gregham's law of diffusion, you have to write here, you have to mark here from the rate of diffusion or effusion is inversely proportional to the square root of molar mass. This statement is called Gregham's law of diffusion or effusion because here they denote a diffusion or effusion. So this is called rate of diffusion or effusion. Up to here you mark it, then mark it rate of diffusion 1 by root m. Then write it for two gases. Mark this and mark up to here. Okay. So this is the answer for Gregham's law of equation. Or if they ask to explain the Gregham's law of equation for 3 mark, then you have to write from write the process, diffusion, effusion and this particles. So what are the marking is done under the heading Gregham's law of diffusion. You have to write it for the question, explain Gregham's law of equation, Gregham's law of diffusion or effusion. Next topic, deviation from ideal gas behavior. So what is the ideal gas and what are the behavior of ideal gas? What is real gas and how it is deviating from ideal gas? We are going to see from this deviation from ideal gas behavior. So for understanding this deviation from ideal gas behavior, you should know what is ideal gas and what is the behavior of ideal gas. So what is ideal gas behavior and what is the ideal gas? Ideal gas is a imaginary gas we assume like, or we derive the condition for the ideal gas is PV is equal to nRT. Okay, so this is the equation for ideal gas. So how you derive this ideal gas equation? From Charles' law, Boyle's law and Avogadro hypothesis. So from these three equation or from these three laws we derive ideal gas equation PV is equal to nRT. So what is ideal gas? Ideal gas is an imaginary gas. The behavior of this ideal gas PV is equal to nRT is comparing with the real gas with this which is exist in our atmosphere or in the earth. Okay, now to understanding this ideal gas behavior or undergo the ideal gas behavior for the real gases. Real gas means what are the gases are exist in our atmosphere? They are real gases. Okay, so what is the condition for ideal gas behavior? First condition, take a box which is filled with air molecules, which is filled with air molecules, only unique air. Unique air means what? Only one air in that box. Okay, so filling one box with the carbon monoxide. Now this is 1 year. So filled that box with carbon monoxide. Now the condition for this carbon monoxide gas, amount of gas is filled in this box. Not only one molecule is present, it contains more molecules in that box. Okay. Now from that carbon monoxide which is filled in the box, carbon monoxide which is filled in the box, okay, this box is filled with carbon monoxide gas. Now take only one molecule from this gas. Okay, from this gas. Now the volume of this carbon monoxide molecule which is occupied in this whole volume of box. Okay, so from this whole volume of box, only one molecule of carbon monoxide occupied volume is negligible. That means it is a small place. Okay, it is a small place. So this is first condition. When gas particles is filled in a place, the one unit of that gas particles or gas molecule which is occupied from that whole volume is negligible. That means it is not under the consideration. We are not considering that is the volume because that is very very small volume of that whole volume. Okay, so that's why the volume of that single molecule which is present in that gas mixture is or gas particles, it is negligible. Okay, we are not taking under the consideration. This is the first condition for ideal gas behavior or for the ideal gas. Okay, then second condition, usually gas particles have no attractive force between the another particle. So this gas particles have no attractive force with the another gas particle CO. Okay, so they are freely moving. They are not connecting together. There is no attractive force with this or any other small attractive force with each molecules. Okay, so this is the second condition for the ideal gas behavior. So what are the condition for the ideal gas behavior? First one, so the single molecule from the whole place, the whole volume, the volume occupied by a single molecule from the whole volume is negligible. And second condition, the gas particles have no attractive force. But actually the real gases, so we already know that this is one imaginary gas. Okay, so we assumed like that. Okay, we assumed that the ideal gas should be like this. Okay, should be under this two condition, but actually real gases are not obeying all the time with this ideal gas behavior. Actually the real gases are not undergoing this ideal gas behavior by in all the condition. You can take one example, liquefaction of gas. Okay, so liquefying the gas are converting into the liquid, that is liquefaction of gas. Now when we convert this liquid into the gas into the liquid, we have to reduce the temperature and applying the pressure. Okay, so reducing temperature and applying the pressure in the carbon monoxide. Now this carbon monoxide gas is undergo the liquid form. Okay, now reducing the temperature of this whole system and applying the pressure into this system. Now applying the pressure means what will happen, the pressure is applying by a piston like this. Applying pressure into this gas. Now what will happen, because of applying the pressure, this piston is moving the gas particles into from here to here. Okay, so the volume of this whole system, the gas particles is occupied in here, they may reduce like this by applying the pressure under reduced temperature. This is piston, pressure applied into it. Now carbon monoxide. Now carbon monoxide is now you can see the difference between these two systems. The particles have some space between each other, but in this system they have very small space between the molecules. That means they have near to each molecules, and because of this small space between the molecules, they have some attractive force between the another gas molecule. Okay, so generally all the gas molecules are not undergo with the ideal gas behavior. So this is real gas behavior only. So there is no gas which is behave in the ideal gas character. So under all the condition, these non-ideal gases are generally known as real gases. But in some places, the real gases are undergo the ideal gas behavior in some condition, only some condition. So this much only. Study Graham's law of diffusion and effusion. Here you have to study what is ideal gas behavior condition and real gas behavior, and what is ideal gas, real gas. Okay, thank you students.